Hello, thank you everyone for coming. So my name is Michael, and I'm very honoured today to be able to present my project to you guys. So anyone here who drives, can I get a show of hands quickly? So we've got a couple of people that drives in, that's perfect. So you might be looking at that and think, what does that mean? Reinforcement learning for multi-intersection traffic light controls with lane area detection range, okay. So don't worry, I'll explain what each sort of component means as we go through the presentation. So a bit about myself, I actually have a background in health and fitness, so I was a personal trainer before. I studied on this course and I did my bachelor's in Solent as well, which is the fitness and personal training. I actually worked in industry for about 2 or 3 years with all kinds of clients, clinical, also like general population and the sports sort of clients as well. And throughout my time at uni, I also started a PT app business which helped personal trainers manage their clienteles, and that's how I got into software engineering. And today I'm working at a company in Bournemouth, building apps, tech for good. That's stuff to do with like climate, deforestation, and just generally tech for good. And one day I was driving back from work actually and stopped at an intersection, and I'm sure others can relate. I find myself sat there on the red light and there was no traffic around. So that was a problem that got me thinking, and after some research and digging around the data, some of the statistics suggested that there was about 356 billion miles traveled in 2019, so these are pre-pandemic figures. And obviously these cause like congestions in like bigger cities or towns, and the side effects of those would obviously be like emissions of pollutants and reduced productivity. People want to get to work, but they're stuck in traffic. And also road accidents as well. So this could help reduce costs if we could help solve these problems. Now currently there are research out there that implements AI solutions to solve traffic problems. And these are typically in the form of reinforcement learning. So just a bit about reinforcement learning. It's very common in the sense that it's, for example, this is an analogy, you are training a dog, and you throw the ball, and you're expecting the dog to play fetch. So if the dog returns the ball, you give it a reward. We say that's a reward of 1. If the dog doesn't return the ball, then we say, you don't get a reward for that. That was not the action that I was hoping for, so you get a reward of 0. So essentially, that's the really high-level overview of what reinforcement learning is. There's many different implementations of it. And much of the research used deep Q learning. So a bit about Q learning is, you can see the agent, which is the dog, and the state or the environment. So for instance, if I throw the ball 10 meters down in that direction, and let's say I want to reward the dog if it goes past 5 meters. So that would be one state, so that'll be one condition. And if the dog gets the ball, then that will get a reward, and then that association would be like a Q value, and we call it a Q value. So essentially the model's trying to maximize or pick the best Q value for the action at that given state. And we use neural networks in deep Q learning to predict the Q values or the Q table, and then pick the best action based off that. So that's just like a really high level overview. But generally we're looking at the literature, and I was just exploring what's kind of the solutions out there at the moment. I found that there was quite a mix of sort of real world and fake road networks used. So some authors opted to go for single intersections or artificially created multiple intersections, which doesn't really correspond to how a real road infrastructure would behave. Some use real world data, but actually assumes global visibility, meaning that the model that they've implemented assumed that they knew where all the vehicles are on the road, which is unrealistic. So my sort of research into this field was to look at adding more constraints to the current literature, adding more constraints to the models, and just limiting the agent in a way so it's more realistic for the real world application. So in terms of my project, so in order to achieve this, I limited detector ranges of traffic lights, cameras, and these are all in the simulation called Simulation of Urban Mobility. So it's the software I've used to do all the simulation. It's open source, you could use it. And limited this to about 15 to 20 meters in detector range, and actually pulled the OpenStreetMaps data from Baker Street, London, just because I was there one day and I was like, oh, it's quite busy around here, so I thought, have a look at that. And actually look on the data for the statistics. It's about 12,000 daily count of traffic at its peak. And the key metrics that I've used to sort of track the performance was average time loss, waiting time, vehicle count, episode reward. So average time loss was basically how much time was wasted when driving at a slower speeds. Waiting time is the time you wasted stopped at intersections, as well as, so vehicle count was how many vehicles were on the road network at the end of the simulation. The episode rewards was more specific towards the AI used, so basically how well the AI performed. And I used three different variants of neural networks inside the DQN. I'll get into that in a minute. But here's a quick demo. And on the left, you can see I've got no AI solution. So that's just fixed timing, fixed intervals, traffic lights run on an interval, 60 seconds on, 60 seconds off. MLP2, which I'll explain what that is in a minute, is an AI solution. And you see those turquoise lines, they're basically detectors. And you can see that's the traffic light intersections as well. So if I play the video, it's frozen. Ooh. I think I might have to scroll through the video for some reason, so it's not loading. Okay, so I don't think it's going to play. Maybe. Oh, there we go. Yes. Okay, perfect. So you skipped out the start. So as you can see on the left side, it's no AI solution. You can see it's quite congested at the moment, and it's now crashed. The AI is too powerful, unfortunately, so I decided to take over the presentation. Okay, let's try that again. Okay, cool. So on the left, you can see now it's like building up. And on the right is the AI solution, and it's starting to get a bit more congested now on the left side. So you can see some traffic stopped on the intersections, whilst the right side with the AI is still flowing quite nicely. So this occurs over about 3,600 time steps, which is equivalent to 1 hour. And I ran this for about 50 episodes, so 50 iterations, training the model. And eventually it gets to the point where there's so much traffic on the road, it gets congested on both, but it's still sorting it out on the right side as well. So looking more for a more quantitative way, we can see that. So MLP2, the number, so MLP will be the AI, the 2 or the 0 and 1 denotes the complexity of the model. Starting from 0, which is very basic, single layer. As you get to 2, you have more layers, and this generalizes the information as it flows through the network. And as you can see, MLP2, the more complex network, reduced the time loss and the vehicle count by about 16% for time loss, 11% for vehicle count at the end of the simulation. Interestingly, it didn't perform as well as a basic model in terms of waiting time. So a more simpler model achieved better results, about 19%, but it's still, the more complex model still achieved a reduction compared to the baseline, which is no AI. And as you can see, you've got the table on the bottom right as well for all the other results. And in conclusion, like I said, so improvements compared to not using AI was observed, and less time lost from driving at slower speeds, less time halted at intersections, so more productivity, less stopped means less pollution, and hopefully less road accidents as well. And in my hypothesis, I've also expected that it would not outperform what's out there currently in literature, just because I've added more constraints to the model and more limitations to how data was being used and observed for the agent. Therefore, it didn't perform as well as what's out there currently in terms of research, but it performed better than a baseline model. So thank you guys for listening. So that's my website if you want to connect. Thank you very much.
Absolutely fantastic. I'm sure you all know that more than 7% of people here drive, and we all face this type of problem. Sitting by the traffic light and just waiting for no reason. So I think some work is done around AI to see how best we could overcome this problem. Any questions, guys? Questions? Yep.
course, yes. So actually looking at the research, mine ties in more into the road infrastructure that's currently existing and sort of like the thing that's already been built. But it's quite interesting to see because there's been some research around smart cities and actually exposing sort of APIs and ways that you could integrate all kinds of data together. So just autonomous vehicles can actually tap into road infrastructure data and sort of algorithms and AI on the edge as well, and to basically optimize the way that it drives or it routes certain like destinations. So it could all tie in through that's what I've seen in the current literature at the moment. So, but yeah, I can see how the AI can be implemented that way as well.
Any other questions? Yep. Pass the mic.
Your sensors, have you compared those to the physical sensors that are already currently in use with road traffic control, such as the magnetic sensors in the road and
Yes, so there's actually quite a different amount of types of sensors available. Some, to my knowledge, are like actuated, and they've got like thermal sensors and everything as well. So at the moment, mine's just comparing just the fixed timing sensors or sort of control systems. They're still common around the road networks, but my research was more looking at adding the limitations to the research that has already implemented the AI in that respect with that road sensor in particular. I guess that could be a limitation and a future design as well, like looking into the future studies. Yeah.
And sorry, did it take into account all traffic or just vehicle traffic?
At the moment, it takes in just cars, but there's the scope actually, and it's quite easy with, but it adds it more complexity with Sumo. Sumo lets you integrate and specify what type of vehicles you like to see on the simulation, such as trucks, pedestrians even. So you could actually have thermal sensors in the simulation, but that just adds more sort of complexity to the network in that sense. And I think still quite a few things that needs to be done around that. But yeah, Sumo does allow that as well. So yeah, perfect.
One more before we go. Any other questions? Yep.
During your research,
Yeah.
did you just focus on reinforcement learning, or did you look at computer vision to solve the problem you're trying to solve? Like computer vision actually detecting amount of cars, if they are pedestrians and all that, and the logic behind that. Did you just focus on reinforcement learning, or did you do your research on computer vision too?
So the question is whether I've just focused on basically the sort of the management of the traffic or the detection.
Beginning you said you were in the traffic, and that's when you decided to solve the problem. So did you, during your research, did you come across computer vision to solve your problem, or was
Yeah.
it just reinforcement learning? How did you arrive at it?
Perfect, yeah. So I came across both computer vision and reinforcement learning. I've noticed that the reinforcement learning, there's still some work that needs to be done, such as the limitation, adding the limitation to the road sensors to make it more realistic in the simulation, so it's more practical to implement. There's quite a lot around the computer vision at the moment for detecting vehicles, so I thought there's a good body of research there already, and I thought just moving into the reinforcement learning side and actually utilizing the results of the computer vision into the reinforcement learning model to help optimize the road traffic. So that was the idea behind that.
It's going to be a very quick one, yeah?
Yeah, Mike,
Yep.
just wanted to ask, in terms of your choice of 50 episodes to train the model, did you come about with that number via the literature review that you conducted, or was it, how did you come up with that specific number?
Yeah, so the literature review, typically about 100, 200 or so, because I was using a simpler model, the MLP, so it actually was much more simpler for me, and the amount of data that I was actually observing, it was just the queue lengths of the vehicle, so it wasn't too complex, so I didn't need that many episodes, and it was just through trial and error as well. 50 episodes worked quite well. It started leveling off the results, so it's cut off at the 50 episodes.
Okay, thank you so much.
Thank you very much.